Hello friends, I welcome you in lecture number 5 on double integral. In this lecture we will discuss one more example on double integral. So before going for that problem, we just understand this rectangular hyperbola, which is a curve in xy plane represented by equation x into y equal to c, where c is a positive constant. So this equation x into y equal to c, where c is a positive constant, represents rectangular hyperbola in the xy plane, and its graph is as shown in this figure. So this is the graph of rectangular hyperbola. It has two branches in first and third quadrant, and we can see that graph is symmetric in first and third quadrant, or graph is symmetric about origin. Now, depending upon the different values of positive constant c, graph will be in different locations. Okay, so we will decide for given value of c, graph will have this type of different shapes. But if we have this equation x into y equal to c, then it will represent rectangular hyperbola, and its graph is as shown here. And depending on the given value of positive constant, we will be able to decide the location of these branches in the xy plane. So with this in mind, we consider this example. Evaluate double integral of x square over the region R, which is the region in the first quadrant bounded by the rectangular hyperbola x into y equal to 16 and the lines y equal to x, y equal to 0 and x equal to 8. So before going for evaluating this integral, we have to decide the limits of integration for x and y, and to find out the limits of integration, we need to sketch the region of integration. And before this sketch of region of integration, we have to decide that at which points all these curves intersect. So if we want to find out intersecting point of these two curves, x, y equal to 16 and y equal to x, we can put y equal to x here. If we put y equal to x in xy equal to 16, we will have x square equal to 16, and that will give us x equal to plus or minus 4. And because y is equal to x, we will have these intersecting points for xy equal to 16 and y equal to x. But our graph is in the first quadrant, so we will not consider this point which is in the third quadrant. We will consider only this point. So that means xy equal to 16 intersect y equal to x at point 4, 4 in the first quadrant. So that we have written here, xy equal to 16 intersects y equal to x at 4, 4, and xy equal to 16 intersects x equal to 8 at point 8, 2. If we put x equal to 8 here in this equation, we will have 8y equal to 16, that will give us y equal to 2. That is xy equal to 16 and line x equal to 8 intersects at point 8, 2. Similarly, y equal to x and x equal to 8 intersect at point 8, 8. So these are the intersecting points of given curves. This y equal to 0 will never intersect at xy equal to 16. xy equal to 16 is the rectangular hyperbola, and it will never intersect either x-axis or y-axis. So with this in mind, we can sketch the region of integration. So we have to sketch the rectangular hyperbola and those three lines. So first we consider, suppose this is xy plane, suppose this is y-axis and this is x-axis, and we have to consider appropriate scales. This is x-axis, that means line y equal to 0, this is y-axis, and we have maximum distance on x-axis is 8 and maximum distance on y-axis is 8. So before writing those intersecting points, I sketch the rectangular hyperbola first. So suppose this is the rectangular hyperbola in the first quadrant. So we approximately assume that this distance is 4 and this distance will be 8, and suppose because this is 4 we can have this is 2, 4, so this point is 4, 4 and this point is say 8, 2 and we require 8, 8 also, so this is 6 and this is going to be 8, so 8, 8 will be somewhere here. So now we sketch all other lines also. We have lines are y equal to 0, x equal to 8 and y equal to x. So x equal to 8 means line passing through origin and passing through 4, 4 and this 8, 8 also. Okay, so we can consider line y equal to x in this way. So this is the line y equal to x, and we are interested in the first quadrant only. This is the parabola x into y equal to 16 and another line is x equal to 8, so it will pass through these points. This point is now 8, 8, so we can approximately consider that this is the line x equal to 8. So this line is x equal to 8. We have y equal to 0, y equal to x and rectangular hyperbola x into y equal to 16. Now our region is nothing but region in the first quadrant bounded by rectangular hyperbola, line x equal to 8, line y equal to x and y equal to 0. So this is the boundary of the line y equal to x. This is the boundary of rectangular hyperbola. This is the boundary of line x equal to 8 and this is the boundary of line y equal to 0. So our region is region in the first quadrant bounded by xy equal to 16 and these three lines y equal to x, x equal to 8 and y equal to 0. So this is the region of integration on which we are asked to find out value of given double integral. So now we have to decide whether we will integrate first with respect to y or with respect to x. Now if you observe the region of integration, suppose we just consider here, this is our region of integration as shown in this figure. So now if we consider vertical line passing through the region in this part, then here vertical line will leave the region at this point which is on the line y equal to x, and if we consider vertical line in this part of the region, then vertical line will leave the region on the hyperbola, and here vertical line will leave the region on the line y equal to x. So the points at which line is leaving the region are not on the same curve. So whenever we have this type of situation, we have to divide the region into two subregions. In earlier problems, whatever problems we have discussed, in those problems our line was entering on the same curve and it was leaving on the same curve. But here up to this point, if we consider vertical lines up to this part of the region, then whatever vertical line we will consider in this part, that will leave the region on the line y equal to x. And if we consider vertical line on this part, then it will leave the region on the rectangular hyperbola. So we have to divide our region into two subregions. Now if we consider horizontal lines, then also we are having this same problem. If we consider horizontal line in this part, then it will leave the region on the hyperbola. But if we consider horizontal line in this part of the region, then it will leave the region on the line x equal to 8. So either we consider horizontal line or vertical line, we have to divide our region of integration into two subregions. So whenever we have this type of situation, we will divide our region into two subregions, and double integral over region R will be equal to double integral over region R1 plus double integral over region R2. So here we can either consider vertical line or horizontal line. Suppose we consider vertical line, then we can see up to this point we are having no problem. If we consider vertical line up to this point, then that vertical line will leave the region on the line y equal to x. So we have to divide the region into two subregions at this point. So we consider a line, perpendicular line or line parallel to y-axis, and we divide our region into two subregions. So one region is which is the region to the left side of this line x equal to 4, and region to the right side of this line x equal to 4. So we can make them separate. This is, suppose this region is region R1, and suppose this is region R2. So we divide our region of integration into two subregions, and we will consider double integral over R1 and double integral over R2. So first we consider the vertical line in this region R1. So if we consider a vertical line in region R1, then our line enters the region at this point, and this point is on x-axis. So we can write that line enters at y equal to 0. Now line is leaving the region at this point, and this point is on the line y equal to x. So here we can write that line leaves the region at y equal to x. Similarly, we consider a vertical line passing through region R2. So this point is on the x-axis. So here there is no problem. Line enters at y equal to 0. So line is entering in the region at the curve y equal to 0, but line is leaving the region in different curves if we consider lines in R1 and R2. Now this point is on the hyperbola xy equal to 16. So from this we obtain y equal to 16 by x. So here we write that line leaves the region at y equal to 16 by x. Now in region R1, the leftmost point of region R1 is origin. At this point value of x is 0, and all these are rightmost points of the region, and at these points value of x is 4. So in region R1 x is running from 0 to 4, and in region R2 this is the leftmost point of region R2. At this point value of x is 4, and this is the all these are rightmost points of the region R2. At all these points value of x is 8. So limits of x are from 4 to 8 for region R2. So now we have to write all these things. We write that we divide the region R of integration into two subregions R1 and R2 as shown in figure which we have sketched. And after that we write down that draw vertical lines passing through R1 and R2. R1 and R2, and we write down what are the limits of integration. So in region R1, so limits of y are from y equal to 0 to y equal to x. So in R1 y is from 0 to y equal to x, and x is from 0 to x equal to 4, because this is the rightmost point of region R1 and this is the leftmost point of region R1. At this point value of x is 0, at this point value of x is 4. Similarly, we write down the limits of integration in region R2. In R2, lower limit for y is 0 and upper limit is 16 by x, and x is from 4 to x equal to 8. So in region R1 we consider this vertical line. This line enters the region at y equal to 0 and it leaves the region at y equal to 16 by x, and this point is the leftmost point of region R2. At this point value of x is 4. All these are rightmost points of the region R2. At all these points value of x is 8. So x is from 4 to 8. So now a double integral of given function which is x square over region R equal to double integral of x square over region R1 plus double integral of x square over region R2. So because we have taken vertical line, first integral is with respect to y. In R1 y is from 0 to x. Here we will consider x as constant, and x is from 0 to 4 plus here x square dy, y is from 0 to 16 by x, then x is from x equal to 4 to 8, and here first integral is with respect to y, so we consider x as constant. Same thing here, while integrating with respect to y, x is considered as constant. So x square is constant, integral of 1 with respect to y is y. So integral is x square into y. Y is from 0 to x. Then we will integrate with respect to x from x equal to 0 to x equal to 4. Here also integral is x square into y, but lower limit upper limits of y are different. Here y is from 0 to 16 by x, and then we integrate with respect to x from x equal to 4 to x equal to 8. First we put y equal to x upper limits, that is we will have x square into x, that is x cube, minus y equal to 0, that is 0. So now this is integral of x cube from x equal to 0 to 4, plus upper limit is 16 by x, so we have x square into 16 by x, and 1 x will cancel out, that is 16 into x minus 0, that is 16x, x is from 4 to 8. Now integral of x cube is x to the power 4 over 4, limits are from 0 to 4, integral of x is x square by 2, and 2 will cancel out, and we have 8 times x square, x is from 4 to 8. For x equal to 4, we will have 4 raised to 4 divided by 4, that is 4 cube minus 0, and here 8 into 8 square, that is 64, minus 8 into 4 square, that is 16. So this is going to be 64, and if we take here we can take 8 into 16 common, so here we will be left with 4, and here we have minus 1. So 64 plus 8 into 16 into 3. So again we can take 64 common. So here 16 into 4, and we will be left with 6. So we have 64 into 7, and 64 into 7 is nothing but 7 into 4, 28 raised to 2, and 42 plus 2, that is 448. So therefore we obtain that double integral of x square over given region R is nothing but 448. So what is new thing in this problem is we had to divide our region into two sub regions. Our region was in this shape, and we have divided our region into two sub regions, and after that we take vertical lines passing through these two sub regions. If we want to integrate with respect to x, then we have to divide our region from this step. This point was 8, 2. So if we want to integrate first with respect to x, we have to divide our region at this point. So this is the line x y equal to 2, and after that we have to consider horizontal lines passing through this region and passing through this region. So if we consider horizontal line in this region, lower limit will be x equal to y, because this line is y equal to x, and here upper limit for x was x equal to 16 by y, because this point is on the rectangular hyperbola xy equal to 16. So x is 16 by y, and in this part lower limit for x is same because it is on the line x equal to y, and here upper limit for x is x equal to 8. Now in this region these are the lowermost points. So at these points value of y is 0, and all these are uppermost points. So for this region we had to consider y from 0 to this point. Y is from 0 to 2. All these points are on the line y equal to 0. That means lower limit for y is 0 and upper limit for y is 2. So in this region y is from 0 to 2, and in this region all these are lowermost points. At all these points value of y is 2, and this is the uppermost point. At this point value of y, and this point is nothing but 4, 4. So value of y at this point is 4. So for this upper sub-region y runs from 2 to 4. Okay, if we consider these lowermost points, at all these points value of y is 2, and at this point, this is the uppermost point of this sub-region. So at this point value of y is 4. So y is from 2 to 4. So if we wish, we can go by considering horizontal lines in this way also. But for horizontal lines we have to divide our region at this point, and for vertical lines we are making separation at this point. So again we just take a look. If we want to consider vertical lines, then we will divide our region from this point, that is at x equal to 4. And if we want to consider vertical lines, if we want to consider horizontal lines, then we will divide our region from this point. So that is our choice in which order we want to integrate first. If we want to integrate with respect to y first, we will consider our region into two sub-regions in this way, and after that we will consider vertical lines passing through these two sub-regions. If we want to integrate first with respect to x, we will divide our region from this point, and then we will consider horizontal lines from these two sub-regions as we have discussed. So I hope you like this lecture, and thank you very much.